Hello, today we will see the production of acetic anhydride and using the Aspen Plus software, and we will simulate the process of this acetic anhydride production. Here we have the problem statement that says, and a treatment of the design of an acetic anhydride manufacturing facility. It is stated that one of the key steps is the vapor phase cracking of acetone to the ketene and methane. So the ketene and the methane is the middle product. So here we have the acetone, and it will be converted, cracked into the ketene and methane. So it says, it further stated that this reaction is first order with respect to acetone, and that the specific reaction rate can be expressed in this ln K, which is equal to 34.34 minus so 34.22 over T. So here we have the original statement, and so in this design it is designed to feed 7,850 kg of acetone per hour is feed into the tubular reactor and tag-full reactor, and if the reactor is an adiabatic and the feed is pure acid, there's nothing except the feed is only acetone, and the inlet temperature is 1035 Kelvin, and the pressure is 162 kilopascal. That means 1.6 atmosphere. And what would be the tubular reactor volume needed to achieve 20% conversion? That means this the first reaction, the conversion of this acetone into these two products, and we are also so it says that acetic anhydride is prepared by the reaction of ethanol, the ketone, and with acetic acid, that is at the temperature of 4255 degrees Celsius and low pressure, that means 0.05 to 0.2 bar. And here we can see that so this the ketone is reacted with the acetic acid, and it's gonna form acetic anhydride. So here we have to do calculate the K value for the reaction constant K value, and also so there are two different ways by which we can define the reaction rate constant to the Aspen Plus environment. We are in the equation 6.2 this equation, and so that in these two forms, one form contains the reference temperature and T naught, and the other does not consider the reference temperature. However, both forms are the output is equivalent, and so let's see take the exponent value for both sides by taking the exponent value for this equation, and then we can have this K, which is equals to e to the power of 34.34 minus and 34,222 over T, and which is equals to e to the power of 34.34 times e to the power of minus 34,222 over T value, and this will be to give us this thing. And then also alternatively the initial time can be arbitrarily chosen, and K that will be calculated accordingly. So let's see that let's take the T initial T value which is equals to 1000 Kelvin, and then the T value can be calculated, so we can replace the T naught and we can calculate the K value, and also the K value can be calculated from this equation. And so finally we can have K which is equal to this amount, and then the first we have to repeat the exponent terms on both sides, and which contain 1 over t terms, to calculate the E value, and then it can be calculated, and the output became this amount. So and now we can calculate using the equations 6.7 and 6.6, and then the K value would be 1.125. And so, and also we can have the alternative K values. We can put also this thing for the K value, or also we can take this thing. So let's start the working on the Aspen Plus. Let's go to the file and new, and we can start with the blank simulation. So here we have the components, the acetone and ketene. This acetone is as a feed component, and it's gonna be cracked into the ketene and methane, and also the acetic acid is being added to form acetic anhydride. So let's click on the next button. So next button is always our lifesaver. Let's choose our method, WILS. Let's change this thing into the all, and now we can choose from WILS and TH method. Let's click on the next button, go to the simulation environment, and then we are told that our process is being held, and the plug flow reactor. The tubular reactor means that's a plug flow reactor. And let's go to the reactors, and from the reactors alternatives we can select the plug flow reactor, and so that we have this one input, that is the acetone, and as an input pure acetone, and as an output we are expecting, so we are trying to achieve the 20%, and so that we will have this acetic anhydride plus we can have the methane plus we can have the ketone. So we can have the acetone, and we can have these three components can be expected in the product side. So let's fill the input components. We are told that the input temperature is 1035 Kelvin. Here we can see that the input temperature is 1035, and the pressure is 1.6 atmosphere, and the pure acetone is introduced as a feed. So the pressure is 1.6, and that's mass flow, and the mass flow is 7,850 kilogram per hour, and the pure acetone is introduced, and so that we can change this thing to the mass fraction. And I can click on the next button, because next button will take you where to go. And we are also told that the reactor is operating an adiabatic. So here we can see the adiabatic. So let's choose the type of the reactor. Our reactor type is the adiabatic, and so let's feed the configuration. The configuration, we are told that the reactor length is 3 meters and the diameter is 1 meter. 3 meters of the length and 1 meter of the diameter. Now we can go to the reactions, and you can click on the reactions. You can click on the new button, and it says R1. You can click on the port now, and then I click on OK. Then click on the new, and in the reactor side, acetone is introduced as a feed, and the coefficient is 1 because we see the reaction they don't have any coefficient. That means 1, their coefficient is 1, and we are also told that the reaction is the first order, so that means the exponent would be 1, and in the product side we have a ketene, and we have also methane. The coefficient is 1 for each of them. Then I can leave this area, and whereas the stick for the kinetics, look, this is the Kmol is 1.125. It's calculated, and sorry, wait a moment. So the A-val is here, so that is you can afford kilojoule per Kmol, and the initial temperature is 1000 degree. It's 1000 Kelvin, and the reactor is operating in a liquid and vapor phase. So if you are running the reactor in a liquid phase, hopefully it will not work. So it's working on the liquid vapor phase. So let's click on the next button, and we can select the R1 and move into the selected directions or to the right side, and still we can click on the next button. So it says overkick into this completed, so that I can run the process and I can see the output, the stream, and if I am achieving 20% conversion or not. I can see also mass balance, energy balance, and also the stream results, and I can easily see everything so the result is ready and it's available. So let's see, I can right click on the plug flow reactor, and I can see the stream variables. So we can see the mole. Okay, that's good. So we can see the input, output. The acetone is introduced as an input, and in the output side you can see there is 107 kilomole of the acetone, and you can see the ketene value here, and also we can also see the methane value. So we can easily see from the mass fractions. So we can see the mass flow, or we can see from the mass fractions how much acetone is there in the product side. So I can show that this is around 80%. That means 20% is converted. That means if this the 20%, that means 20% is converted. So the process is satisfying our objective. So at the result area, I can see the temperature, input temperature, the output temperature, and also the retention time is here. So for now, I have to stop here, and so we'll continue the production of acetic anhydride on the next video. Have a good time.